last speaker of the last day is Minjae Cho from the Princeton. He will give a talk on the bootstrapping the Ising model on the lattice. Please welcome.
Thank you very much. Thank you very much for the opportunity to speak here. I really wish I were there in person, especially given that Pohang is almost right next to my hometown Busan. And my parents would have been very happy to see me. But unfortunately, I couldn't make it, but organizers kindly understood my situation and allowed me to present remotely. So thank you very much. So today I'm going to tell you about another bootstrap example. And this is based on my work this summer together with my collaborators here. And it's about bootstrapping the Ising model on the lattice. And when I say Ising model here, I literally mean the good old Ising model that we first encounter in statistical mechanics course. So you might wonder, like, okay, what new things are to be learned in the case of this good old Ising model? Well, let's move on to the motivation part. So first of all, we know that statistical Ising is interesting prototype of ferromagnetism. So there is a physics motivation to study the system. And there are actually a few analytically solved cases. So they include 1D with or without the external magnetic field. And in 2D case, you're solved for the zero external magnetic field, which famously has the phase transition. But it also turns out that even though the problem is very old and it's very simple, there are still analytically unsolved cases, such as 2D with non-zero external magnetic field, and 3D with or without the external magnetic field, even though we understand by now via conformal bootstrap the 3D at the criticality. But away from that, our understanding is mostly coming from the numerical simulation. So one might ask, how do we approach such unsolved cases? Yeah, sure.
Yeah, so you said the 2D with non-zero external magnetic field is not solved. But actually,
well, yeah.
I mean, Sasha Chamorachko.
Oh, sorry. So that is for the Ising field theory. And there, I think you have in mind.
If you take the continuum limit, it should be identical.
Oh, sure. So here I'm just talking about the lattice case. And Sasha Zamolozhikov studied this problem using the conformal truncation method, right?
No, that's not true.
Sorry, are you talking about the E8 theory?
Yes, it's nothing to do with conformal truncation.
No. In the E8 case, one is actually turning on just the magnetic field, but without the massive deformation, right? In the ICCFT, there are two relevant.
Yeah, so temperature is T equal to TC. So you are saying that both T is not same as TC and H is non-zero?
Exactly. I'm actually studying most general temperature.
Okay, in that case, that's true. But you didn't mention on this slide that you're considering only T is not same as TC.
Yeah. I mean, yeah, if you wish, let me say it now. So I'm going to consider general temperature and general external magnetic field.
Okay.
Any other questions? Yeah, thanks for the question. So how do we study such cases? There is one classic method, which is Monte Carlo simulation. And this is what we learn in STEM course as a grad student. And using this, we can actually get some estimates about the spin correlators and thermodynamic quantities. And the second way to study this are actually using the analytic inequalities. Okay. For example, you can look at the classic book by Gleam and Jeffy, or in the 70s and 80s, there have been a lot of works by great physicists like Michael Eigenmann, Barry Simon, Elliott, and other collaborators. And they used, either reflection positivity or Griffiths inequality type inequalities to put bounds on some of the interesting quantities. And, modern bootstrappers, if they first run into this statement about inequalities, now they start to wonder if there is a way to incorporate this story into the modern bootstrap perspective. Okay, and that's basically what I'm going to tell you today. Of course, in bootstrap, we know that at least in numerical bootstrap, we require some positivity. And there should be also some type of relation in the CFT is say conformal block where the descendant structure is dictated by the primary. And before I jump into the specifics of the Ising model, I wish to list some of the examples in the literature using this idea. So of course we have conformal bootstrap and S-matrix bootstrap. Also we just heard a very nice talk from James about the hyperbolic bootstrap. Here there are also other lists. So the first work that I want to point out is the work by David Goluskin and collaborators. Actually, these people are applied mathematicians. So they never use the word bootstrap in their paper. But if you look into their paper, you can see that they are actually bootstrapping classical dynamical systems, okay, using positivity and relations between the time averaged values. So yeah, that's a very interesting and impressive work, which I want to introduce to you. And actually, Vladimir, during this workshop, gave talk on another subject, but he also wrote down together with Zhichen Jia early this year a very beautiful result on bootstrapping the large and lattice gauge theory using reflection positivity, square, and loop equations. And also, similar story is present for the large matrix integral or quantum mechanics, which was initiated by Henry Lin. And by now, for the last 2 years, there have been numerous papers on the bootstrapping quantum mechanical systems. And today, I wish to add on this list the case of statistical mechanics. Okay. Well, the simplest model that we learn in STEM course is, again, the Ising model. And today, my goal is to bootstrap Ising model on infinite cubic lattice. So by cubic, I mean generic hypercubes. So the story applies to generic dimensions. So for example, in 2D, we are dealing with a square lattice. And okay, first of all, let me define the lattice. It's the cubic lattice, meaning that we have unit vectors. There are D of them. Okay, it's D-dimensional. And then we take the integer linear combination of them. And that defines my lattice. And the partition function is given by summing over each point on the lattice. And on each point on the lattice, we have the spin variable, which can take value only +1 or -1. Okay. And the probability measure is given by this, this expression, where the Hamiltonian is given by this nearest neighbor interaction term. So this square bracket stands for the nearest neighbor pair. Together with the coefficient J. So again, to clarify, I'm not studying things at critical temperature. Okay. And also, I'm going to consider generic magnetic field. Oh, sorry, was there any question?
Just go ahead.
Yeah. And also, I'm going to focus on the ferromagnetic case where J is greater than or equal to 0. Okay. This is where the some of the reflection positivities and other non-trivial inequalities can be shown to hold true. I'm going to choose H to be positive. This is actually just a convention because I can always flip the sign of the entire spins. Then that will also be equivalent to changing the sign of H. Okay, a few more notations. So say we are given some finite subset A of this lattice. Okay. And then by S under by A, what I'm going to mean by that is product of all the spin variables where this X ranges over this subset A. Okay. So when A is, for example, given by these 3 points, origin 1,0 and 1,1, then just like in this picture, then S under by A is simply product of all these spin operators. Okay. And the spin correlator is defined by 1 over the partition function times this S under by A evaluated together with this probability measure. Okay. And these spin correlators are going to be the object to be bootstrapped today. Of course, now we have this lattice and there are some symmetries. So not all the spin correlators are all independent. The ones which are related by symmetry are actually the same. And in the square case, for example, we have dihedral group together with the translation. And in 3D case, for example, we have yeah, we have the corresponding spatial symmetry group. So for example, let's look at this, nearest neighbor correlators. If we have as origin and as 1,0, that by rotation is the same as the one which is stretching vertically. And also by translation, we can translate it by 1 unit, but the spin correlators are the same. Okay. Now, let me tell you something I will call relation. Okay. So by relation, what I mean is some relation that holds between different spin correlators. So actually, this symmetry case is one such example because this is a relation between seemingly different spin configurations. But there are actually somewhat way more non-trivial ones. And they are analog of either Schwinger-Dyson equation or equations of motions or loop equation in different contexts. So let me explain why I call them like that. So let's fix a point P in the lattice. Okay, this is a single point in the lattice. And now we are going to take change of the summation variable SP to minus SP in the partition sum. Okay, so in this summation, we are going to change SP to minus SP. Okay, and because this is merely change of summation variable, the result should remain the same. Okay, so in particular, all of these spin correlators should remain the same under this change of variable. But the non-triviality comes from the fact that if we actually take the change of variable, the expression for this guy is actually going to take different form. Okay. So for example, our S underbar A, the variable itself, can obtain a sign, minus sign, if P, the point P is part of A. If it doesn't include P, then there's no sign obtained. And let's also look at the magnetic field part, okay? This is sum over all the spin variables over all the lattice, but the point P now has different sign. So this is going to be the result, which one can also express in this way. And one can do similar thing for the nearest neighbor interaction, okay? Whenever the nearest neighbor interaction term includes the point P, it's going to take this extra term. Okay. By the way, I have to mention, we are not the first one to discover this. Of course, this was discussed a long time ago, like 5 decades ago. And these are some of the papers discussing them. So end result is what we call spin flip equation. Okay. What it's saying is that, okay, I had originally some spin correlator, but now I take change of variable from SP to minus SP. Then the result is this right-hand side. And this is a non-trivial equation which holds between seemingly different spin correlators. And now you see the similarity between the usual, say, Schwinger-Dyson equation or equations of motions, because those are the ones which we obtain by taking the variation, infinitesimal variation of the integration variable. And in this case, the analog of integration is basically this summation. So you might complain that on the left-hand side, we have some finite degree polynomial expression in terms of the spin variables, while on the right-hand side, we have exponential. But the thing is that Ising is nice because once we Taylor expand this exponential, it's actually going to truncate at some finite degree. It's simply because the spin variables can take the values +1 or -1 only. Okay. So the simplest example here is the magnetic field term. Okay, for the SOP. Once we Taylor expand it, we are going to get 1 plus SP squared term and da. But because SP squared is 1 always, it's going to truncate at the linear level. And similar argument holds for the nearest neighbor case. Okay, once we expand it, we are going to end up with some finite degree polynomial. So what then it's saying is that basically this spin flip equation gives relation between different finite degree polynomial expressions of the spin variables. So let me give you an example, okay? So this is square case, d equals 2. And we are setting the magnetic field to be 0. So in this case, I'm going to assume that all powers of spin variables are going to be 0, So I'm going to assume Z2 symmetry. And for the spin flip, the site for this spin flip, let me take the origin. And the spin correlator of interest, let me take it to be the empty set. So the expectation value of empty set is, of course, 1. And here's a pictorially what's happening. So this green dot, which is the origin, is the location where we are taking the spin flip. But once we take the spin flip, what's going to happen is that because of the nearest neighbor interaction term, it's going to now bring down this nearest neighbor terms in this spin flip equation. And the end result looks like this. Okay, so here A and B's are some known functions in terms of some hyperbolic functions in terms of the temperature or equivalent to J. As you can see, there are different spin correlators arising in this spin flip equation. So this is an equation telling you which relation is satisfied by different spin correlators. Okay. Let me tell you, even though I just focused on this small region, this equation is rigorous. I didn't take any approximation to finite size lattice or anything like that. Okay. So let me do some counting. Okay. So in 2D case, we are going to consider something that I unfortunately named 13531 diamond. It has this long name simply because when I first realized the importance of diamonds in this story, I just called it 13531 and that just became the name. So what we are going to do is to consider all possible spin configurations within this diamond. Okay, so there are in total 13 sites. So we a priori have 2 to the 13 possible spin configurations. But then what I'm going to do is to take this spin flip equation where I take the spin flips only for this green dot. Okay, just one green dot at each time. Then I'm going to get spin flip equation, which is going to be closed within this bigger diamond, 13531 diamond. Okay, and that gives me some equations that I can solve. So let's look at, for example, non-zero magnetic field case. So again, we start with 2 to the 13 possible configuration. And after taking into account all the symmetries of the lattice, we are going to end up with something like 10 to the 3 number of independent spin correlators. But it turns out that most of them are actually dependent on each other via the spin flip equations. They're about the same order of spin flip equations. And once you solve these spin flip equations, you're going to be left with only 29 independent spin correlators, even though you started with 2 to the 13 to begin with. So this is a drastic, drastic reduction in the number of these spin correlators that we have to consider. Okay, and there are other cases. For example, in 3D, one can consider, for example, what I call 1551 diamond. So in this case now, the nearest neighbor can extend in all the 3 directions. So that's the reason for considering this type of diamond. And in this case, as you can see, we have 2 to the 12 configuration to begin with. But after taking into account symmetry and the spin flip equations, we are left with only 51. And this is the largest configuration that we consider. So the most symmetric one that's close to this one is actually 151351. But there was just too huge a numerical problem for our current algorithm, even though it might be doable in the future. So we just consider this 15551. And in that case, there are 2 to the 17 variables to begin with. But after using all the symmetry and independent spin flip equations, we are left with 629. Okay. By the way, I have to mention that this spin flip equation is actually a linear equation. Okay, it's linear in the spin correlators. And that is actually what's going to make the numerical analysis pretty convenient. Okay, before I go to the positivity, are there any questions about spin flip equations so far? Okay, good. So now let me go to positivity. Well, positivity is the star of the bootstrap, as always. And turns out the Ising model has infinitely many interesting positivity conditions. And today I'm going to tell you only 3 of them, unfortunately. But 3 of them are already powerful enough for some purposes. The first thing is what we call square positivity, okay? And all it's saying is that real number squared is positive. I mean, to be rigorous, non-negative. So we are going to consider some general linear combination of the spin operators together with the real coefficients, okay? And of course, if we square this expression, it should be positive because everything is real here, as this spin variable takes only plus minus 1 values, and all these coefficients are real. And the measure that we are using for this Ising model is also positive. Okay. So the end result is that, okay, this operator expression squared is positive. Okay. This is a non-trivial positivity, but it turns out that empirically, this positivity is actually implied by other positivities, which I'm going to discuss. We don't have a proof for this, but we just observe this empirically. The second set of positivities or inequalities that I'm going to consider is something called Griffiths inequalities. And if you want a short, brief introduction to this, you can look at this classic textbook by Glim and Jeffy. They have nice discussion of this and implications. There are actually infinitely many Griffiths inequalities, but I'm going to talk about only 2 of them. The first Griffith inequality and the second Griffith inequality. The first Griffith inequality simply says that all the spin correlators must be positive, okay, with the assumption of the ferromagnetism. And this is actually easy to see. So we can express this thing in the background of the zero coupling, okay? So in the zero coupling, now we can consider this major factor as also something that's to be evaluated inside the correlator. And then, because we are at zero coupling, this expression is going to be non-zero only when all these spin variables are gone. Okay. But once you think about Taylor expanding this exponential, it's going to involve only powers of j and h with the positive coefficients, and j and h are positive. So this expression is going to be positive. Okay. And there is also something called second Griffiths inequality. And it goes like this. So take any subset A and B of the lattice. Okay. And what it's saying is that the correlator of spin variables at A and B is greater than or equal to the product of the spin correlator of A and spin correlator of B. Okay. But notice that this inequality is actually non-convex. And for that reason, when we are running the bootstrap later, we are actually not going to impose this. But interestingly, we'll see that if we are able to incorporate this second Griffiths inequality, we'll actually get better bounds. And I'm going to discuss this later. One thing I forgot to mention. So this first Griffiths inequality is linear, as you can see. So it is going to be incorporated in our bootstrap later. And finally, we are here to...
Can I have a question?
Sure.
In previous slide, in case 1,
Yeah.
if you consider just single side chain, I mean point, S goes to minus S is the symmetry, is it?
Only in the absence of the magnetic field.
Yes, so but anyway, this positivity seems that I don't understand. So I can change S. S can be either 1 or minus 1.
Right.
In single side.
Right.
So how it can be positive definite?
So, okay, in the zero coupling, once you sum over +1 and -1, you get 0.
So this average means that sum of all possible SA states.
Exactly.
Okay. Okay,
Yeah.
thanks.
Yeah, thank you for the question. Yeah, sometimes, you know, like, yeah, it might be confusing when you consider the values that spin operators can take versus their averages. But yeah, in this case, all the positivity conditions that I'm stating are at the level of the actually averaging or the correlation. Thank you for the question. So our last positivity is nothing but the reflection positivity, which had great success in, say, conformal bootstrap. And it's not surprising that we are running into reflection positivity and the power of it in this case. So in order to talk about reflection positivity, I have to first tell you which reflections I'm going to consider. I'm going to consider only the reflections which preserve the lattice, okay? And it turns out that in 2D or higher dimension, there are only 3 types, okay? So even though I have figures only for 2D here, there are only these 3 types of reflections even in higher D. It's just that reflection axis will be now reflection hyperplanes, okay? So the first reflection is the reflection along the vertical axis, which is going through the site, okay? And in particular, I'm going to consider the spin configurations on the left half space, which includes the axis, okay? So if I have this half space configuration given by these green dots, 3 green dots, once I reflect them, I'm going to get these 3 blue dots, okay? And the second reflection is the offside vertical reflection. Again, if I have some half plane configuration, these green dots, then they are going to get reflected to these blue dots on the right half. And the last reflection is the on-side diagonal reflection. Okay. Again, they can, now the half configurations can sit along the reflection axis. And if I reflect these green dots, I get blue dots. So what are good for, what are the good things about these reflections is that they actually give rise to positivity, okay? And I'm going to illustrate this only for the first type of reflection, but the story is very similar for the second and third type of the reflections. So let me focus on the first reflection, which is the vertical reflection, which is stretching along the sides, okay? Here, there are some notations. So P stands for the sides along this axis, okay? And H1 stands for the left half space, which in particular, again, includes the space P. And then we are going to have the reflected half plane on the right, which again includes this P. And that's going to be denoted by R1 of H1. Okay. And now we are going to consider some half space spin configurations. Okay. So this O is now some real coefficient, real linear combination of spin configurations where the spins are allowed to be seated only on the left half plane. Okay. And once we reflect it, we are going to have this expression where we still have the same real coefficients, but now the spin variables are sitting on the right half. Okay. And we can take any real coefficients here. And the claim is that for any real coefficient that we take here, if we take product of these two and take the average, that's going to be positive. And this is what we mean by reflection positivity. Okay. So how does the proof go like? It's actually pretty simple. So the first thing which we are going to do is to, in the sum, we are going to separate out the reflection axis. Okay, so we are going to separate out this sum. And there's this measure factor, which is purely realized on the reflection axis. Okay. And then what about the rest? The rest is what I'm going to call psi of S of P. Okay. So they are basically something that we obtain once we sum over the left half plane. Now subtract with the subtraction of this reflection axis. Okay. Due to the nearest neighbor interaction here, even if we sum over all the spins on the left half, we are going to end up with some function which depends on the spin variables along the reflection axis. And that's what I'm going to call psi of S of P. Now, you can do the similar thing on the right half plane. But the thing is that because this operator itself is defined by reflection, that end result of summing over the right half should be the same. It should be the same function. That's the reason why here we have psi squared. Now you see that this is positive, so this quantity is positive. Okay. So this is reflection positivity. There is actually an equivalent way to write this down. in terms of positive semi-definiteness of a matrix. So I'm going to define metrics associated with this reflection positivity. Okay. So the matrix, the elements are labeled by subsets A and B of the left half plane. Okay. So by this, the matrix element is going to be the average of spin variables of A, which is situated on the left half plane. But for the B, I'm going to let them be reflected to the right half plane. And I'm going to take this as my matrix element. And the statement of reflection positivity can be easily seen to be equivalent to the positive semi-definiteness of this matrix. And note that this matrix element is a linear expression in terms of the spin correlator. And this linearity is what makes the semi-definite programming possible. So good, reflection positivity is good, and people actually used it to derive non-trivial results. For example, the existence or non-existence of phase transitions in various cases. But I'm going to actually combine this with the relation which I described before, which is the spin flip equation. Okay. So here I'm again giving you the example of the 2D, but you can do similar exercise for the higher D. So, again, I'm going to consider the spin configurations confined to this diamond, 13531, and the spin flips are taken for this inner diamond, green dots. And spin flip equations basically give rise to some linear relation between different spin correlators. And once one solves it, any spin correlator in this domain can be expressed as a linear combination of something I will call independent variables, which we obtain after solving for the spin flip equation. Okay, and because the spin flip equation was linear, these are linearly related. Okay, so again, for non-zero magnetic field in 2D, the number of these independent variables was just 29, if you remember. Now, what we are going to do is that, okay, we built these reflection positivity matrices, and they have some matrix elements which are generically of this form. And now we are going to substitute this expression into those matrix elements. And the end result is the following. Because of linearity, again, this matrix is also going to be linear in the independent variables. Okay. So this is the positivity condition that we have. And recall that there are 3 reflections that we consider. In addition, another linear relation was given by first Griffiths inequality. So for any spin configuration, we can express it using the spin flip equation as some linear combination of independent variables, and that should be positive. Okay. And once you see this positive definite matrix, which is linear in the variables, and if you bring this problem to your optimization friend, he or she will tell you that, oh, this is an easy problem to solve. And this is nothing but the semi-definite programming problem. So the statement of the SDP, semi-definite programming, is minimize or maximize some linear combination of your variables subject to the positive conditions, which is again linear in your variables. Okay. And yeah, this is, for example, what can be solved by SDPB that James mentioned. But in our case, we are using some different solvers, either Mosaic or SDPAQD. So SDPAQD, here QD stands for quadruple double precision. And we actually encountered that this amount of high precision was actually required for us to get good bounds and stability. Any question? Okay, good. So now we can simply plug our problem into the SDP solver and see what we get. So first thing first, there is analytic understanding for the zero external magnetic field case. So let's first compare with the exact thing. Okay. So here I'm going to assume Z2 symmetry, meaning that all the old spin variables will be set to be 0 from to begin with. And the simplest non-trivial correlator that I can look at is the nearest neighbor correlator. Okay. This is nothing but, I mean, it's basically the free energy. And along the x-axis, I'm plotting J, which is inverse temperature. And famously, there is this critical temperature, JC. And here, black line is the exact result, the analytic result. And you can see these green dots, okay? These green dots are upper and lower bound, which is derived from this very small, tiny diamond, 131. And finally, the blue dots are the lower and upper bounds derived from 13531 diamond that I have been discussing. And as you can see, we just increase the diamond size by 1, but the bound increases a lot. And again, this is a rigorous result on the infinite lattice. We didn't do any approximation. This is rigorous bound. You can take it as a mathematical proof. And the bootstrap allowed region is this blue region. And you can see that away from criticality, it shrinks pretty quickly. And near criticality, it's kind of expected that the bound is not as good because the correlation length diverges, and we are considering just the finite set of the spin correlators. But I mean, just from the improvement from the previous diamond, you can kind of expect that if you increase the size just by 1, it might be almost indistinguishable by eyes. And here we are also plotting the next to nearest neighbor spin correlator, and the bound is still good.
So how far can you increase the size?
Good question. So I'm actually going to comment on that later. But so if you increase the size, if you naively take all possible spin configurations and solve the spin flip equations and repeat the exercise, probably it's going to be beyond our current numerical algorithms power. But you might actually wonder if there are some subset of those configurations which might be good enough in the sense that they are still going to give rise to the bounds which are of the same order as the ones where you consider the full set of the spins. So that is to be explored. Yeah, we didn't explore it too much, but you kind of get the sense about how good this thing can be if you increase the number of the variables under consideration. Good. Let me compare with.
Can I have another question?
Sure.
So when H equals 0, still, and you are considering J to be different from JC.
Mm-hmm.
And in that case, it is known that this correlation function should be given by some massive decay. No.
Oh, right. You're talking about the exponential decay of the correlators.
That's right. So can you see that?
Great. Yeah, indeed. So you can think of this as a complementary way to complementary approach to such questions. So what I mean is the following. So if you actually look into the papers written in 70s and 80s, they prove this exponential fall-off behavior of the criticality using nothing but the Griffiths inequalities that I mentioned. There are actually more general versions of that, and actually people like Barry Simon, Michael Eigenmann, and Elliott used such Griffiths type inequalities to prove the exponential decay of the correlators. Here, by construction, I was considering only this spin variables within this small size domain. So I cannot directly give you the bounds on the long range correlators. But actually, that's one of the future directions one can consider, which is that you can consider that some large space of you simply extend this diamond just horizontally, not vertically. There are still good spin flip equations, and you might consider some subset of the entire spin configurations, because what you will be interested in is just the correlator of pair of spins. And in that case, is there something useful to say regarding these bounds? Well, we didn't try, but that's one possible future direction.
But it seems
So yeah,
these two difference of these two graphs is that you are increasing the distance by 2 units.
Oh yeah, here is only nearest neighbor to the next nearest neighbor, so it's still short range if you wish.
Yeah, okay. So you can increase this a little bit further. Let's see.
Yeah, so with our current approach, it's actually hard to directly put the bounds on the long range correlator because we have to then increase our size of the domain. But I have actually some more comments on that later. Again, yeah, this is coming from some of the intuitions from the papers in the 70s and 80s, where people actually proved the exponential follow-up using the Griffiths type inequalities. So, okay, probably I can mention it now. So these general types of Griffiths inequalities, they are non-convex. And that's the reason why we cannot plug it into SDP. But famously, non-convex inequalities, some of them have nice convex relaxation methods, okay? So one can ask if one can incorporate such things. And that's one of the things that we are currently wondering about.
So if I just add one comment, if you could do that, then this exponential decay coefficients in the exponent has been exactly known that because the mass scale is exactly known in terms of this J minus JC number. Mm-hmm. So and yeah. that is a quite interesting check.
Indeed. Yeah, I completely agree. Yeah. Thank you for the comment. Okay. So in this, already known case, let's do another comparison. Now this is comparison against Monte Carlo. So this green and blue are basically the discrepancy of our bootstrap bounds from the exact answer. Okay. And this orange and red are the Monte Carlo 1 sigma error bar after about 1,000,000 time sweeps using Metropolis algorithm. And you can see that they're kind of compatible, and away from criticality, Bootstrap is doing better. But again, I wish to emphasize that Bootstrap bounds are exact. I mean, they're rigorous, okay? While Monte Carlo estimates are estimates. Okay, you might wonder, can we see spontaneous magnetization? One of the fascinating thing about zero external magnetic field is that there is a phase transition. Okay, and phase transition, the order parameter is given by the magnetization, which is nothing but the correlator of a single spin. Okay, so in this case, at the level of the bootstrap, we can simply not assume Z to symmetry. So we just do not set these type of things to be zero and see what we get. And this is a plot for the upper bound coming from the bootstrap. So this gray is the exact answer, exactly known answer. I'm plotting different regions together with or without the Griffiths inequality, the first one, okay? So these black circles are 1, 3, 1 bound without the Griffiths inequality. But once you actually include the Griffiths inequality, now you see this striking cutoff, okay? And this is actually something one can prove analytically using first Griffiths inequality, saying the upper bound on the magnetization is exactly 0. And that's what we observe here. Now one can consider 13531 without first Griffiths inequality. It's pretty good. If you include the first Griffiths inequality, it gets slightly better. And around this area, they are roughly the same as the exact answer. So now let's move on to the case where we have no analytic understanding of these correlators. So this is in the absence of the magnetic field. In the presence of the magnetic field. Okay. So I'm plotting the nearest neighbor correlator as a function of two couplings, J and H. Okay. And the color sheet here is basically the upper bound. While you can see this slightly different grid underneath. They are the lower bounds. It's just that once one turn on the magnetic field a little bit high enough, then the discrepancy between the upper and lower bounds are almost indistinguishable. And that is actually represented in this color plot. Okay, what does this color mean? They are the upper bound minus the lower bound. Okay. Around this red and orange region, they're roughly like of order 0.1 to 0.001. But this yellow region already is something like 10 to the minus 6 or 7. And when you go to your Monte Carlo friend, they will typically tell you that the significant digits that they can get are only 5 or 6. So this yellow region is already doing better than Monte Carlo, typical Monte Carlo. And now what is this deep blue region? That's where the discrepancy is 10 to the minus 15 or less. Okay, so you see very high precision of the numerical bootstrap. And by the way, you might wonder why is it that along this line, the bound is not good? It was actually explained nicely in this old paper. It's just that once you turn on magnetic field, there's now a new length scale. And this length scale is to be compared with the size of the diamond that we are dealing with. So, okay, this might not be too visible. So let's take a slice of the previous plot. We are going to take J value to be J critical. There's nothing sacred about it in the presence of the magnetic field, but we choose just a slice. And again, this is the difference between upper and lower bound. That's the blue dots here. And this red dot is basically the Monte Carlo 1 sigma error bar. And you can see that as magnetic field increases, Bootstrap is far better than Monte Carlo. And on the right-hand side, I'm plotting some of the things. It might be a bit hard to understand this, but the only comment I want to make about this plot is that, so these are basically the Monte Carlo error bars. And when they do not have overlap with this axis, that's where 1 sigma Monte Carlo result is completely outside the Bootstrap bound. Okay, in other words, Bootstrap is ruling out some of the 1 sigma Monte Carlo results. And if you include up to 3 sigma, then everything is within the Bootstrap bounds or compatible with Bootstrap bounds. One thing I want to mention is something we called deep feature. Okay, so now this is for some small magnetic field, and we are varying J. Okay, and you can actually see that there is some non-monotonic behavior in the lower bound from Bootstrap. Actually, if you check the solution of the SDP problem and plug those values into the second Griffiths inequality, you can see that those inequalities are violated. So this non-monotonicity is actually associated with the violation of second Griffiths inequality. And there's actually a consistent statement in the literature, for example, in this textbook by Glim and Jeffy, which is saying that first and second Griffiths inequalities imply monotonicity of spin correlators as a function of the couplings. So it makes sense that because we didn't take into account the second Griffiths inequality, it's not in contradiction with the fact that we are getting non-monotonic behavior. In other words, if we find a systematic way to incorporate the second Griffiths inequality, this bound will actually get better and will be monotonic. And finally, this is preliminary result for the 3D in the absence of the magnetic field. So famously, this again has phase transition somewhere. Even that temperature is not known. But I mean, yeah, conformal bootstrap is the way to solve the system at criticality. But now we are just looking even away from criticality. And there are, so this red line is the Monte Carlo result. And these dots are basically bootstrap bounds. The strongest one we get from 15551, but it turns out that even that is already too big a numerical problem for our SDP solvers to handle. So we simply looked at some truncated version of the reflection positivity. And the bound we get is this. But again, this truncation still maintains the rigor of the bootstrap bounds. Okay. So this blue region is the bootstrap all-out region and is nicely compatible with the Monte Carlo result. And this is still preliminary. So when I say it's preliminary, I have to tell you about some thoughts about improving the numerics. So here are now some thoughts, and I'll end after this. So basically, this is something that I already mentioned, but one can ask, what are the relevant subset of spin configurations? Rather than considering all possible spin configurations in some given domain, there might be some relevant ones which are good enough in the sense that they give the bounds which are of the same order as one considers the full set of the spin correlators. And also there's a question about how to generate spin flip equations more efficiently. Another possibly related thing, but conceptually also interesting, is something we call null states. Okay, by null states, all I mean is that we have reflection positivity matrices, and those matrices can have eigenvector with 0 eigenvalue. And these eigenvectors are associated with some linear combination of the half spin configurations. And those spin configurations, those linear combinations are what we are going to call null states. Okay. So recall that in our SDP problem, we were either maximizing or minimizing some spin correlator under the positivity assumption about these matrices. And it's very likely that the bounds are going to be obtained when this is roughly 0, meaning that it obtains just the nearly 0 eigenvalue. Okay. So once we get such a solution, we can evaluate the matrix. And now this is a C function matrix. This is now C number matrix, literally. And when the bounds are tight, these two matrices are roughly equal to each other. And now, when we look at null states of these guys, it means that even in the exact theory have some rough null states, which is linear combination of the half spanning configurations. And because they are null, now if we consider this type of spin correlator, which is basically the semi-norm of this spin, this null state, it is roughly 0. And by Cauchy-Schwarz, one can argue that this thing, when one computes the inner product against any other spin half space spin configurations, it is also going to be 0. So in that sense, it's really like a null state. So one might say, oh, what is this? Okay, and we don't have rigorous way to, we didn't phrase it rigorously yet, but there is one nice thing that we can think of, which is OP relations in the usual quantum field theory. Okay, so when you think about this type of expression, all it's saying is that when you have huge number of spin configurations, that can be approximated by linear combination of some other smaller number of spins. And that's roughly like the OPE, even though we do not yet have any rigorous understanding of this. So once one has this null states, one can ask, can these be used to improve the numerics? Because now we have some extra inequalities or rough inequalities that we can impose. So that's one question. And finally, let me tell you about a suggestion made by Michael Eigenmann and Elliott. So I was very fortunate because I presented this work at Princeton in one of the informal lunch talks. And there were these two giants at Princeton, Michael Eigenmann and Elliott, in the audience. And they were the ones who told me that they've done all these amazing works in the 70s and 80s, and it might be nice to combine the modern bootstrap method with their old analytic works. And this is something that I already mentioned, but there are basically infinitely many inequalities, but the immediate obstacle is that most of them are non-convex. But one can ask if there are good enough convex relaxations of these inequalities, and they can actually improve the bounds, or even further, give some implications about long-range correlators and so on. So that's an open question. With that, let me end, and thank you for listening.
Thank you very much for the talk. Yes, please ask a question.
Yeah, I have a few questions. So in your graph, how much is the error bar?
In my graph, error bar.
Yeah, because in that graph.
For example, here.
Yeah, for example.
So again, I want to distinguish the error bar. So when you say error bar, you mean Monte Carlo or Bootstrap?
I don't know, but how much do you trust in these numbers? I mean, there should be some combined error or whatever.
No, there is no error bar in Bootstrap bounds. Bootstrap bounds are rigorous. We only have upper bound and lower bound. And the statement is that it's mathematically proven that the exact value should lie between this upper bound and lower bound. That's the power of Bootstrap. There is no estimate.
So what is upper bound and what is lower bound in these graphs?
So lower bound is shown here. And this blue region is the region between upper and lower bound. And in this case, you can hardly distinguish the upper and lower bound.
Almost overlapping, right? These two bounds are overlapping in the graphs?
Yeah, so in this case, you cannot distinguish them by eyes. I mean, explanation for that is that this is a difference between upper and lower bound. And you can see that it goes all the way to 10 to the minus 15. That's the reason why human eye cannot distinguish them.
Okay, good. Then, first of all, can I ask this question about this? Is the bump you showed in the previous graph?
Deep?
Yeah, deep. Yeah, in the first graph.
Yeah.
This is H is 0.03, and then the distance from the critical value in J, where J minus JC is around 0.1 or 0.2 or something like that.
Yeah, something like points, order of
Right.
0.0. Yeah, something. Yeah.
So does this mean that I can assume that this scale J minus JC is somewhat bigger than H?
Ah, good, good, good. Indeed, this relates to my previous point about the appearance of the new scale, because we turned on the magnetic field H. Now there's new scale. And indeed, this is where the new scale, new length scale, is about the roughly the same size as the domain of the domain under the consideration for the bootstrap bound. And that's exactly the reason why bootstrap bound is actually weaker. So indeed, yeah, indeed.
Yeah, because that reminds me some field theory based research with two deformations.
Right.
J is different from JC and H is non-zero. And
right.
depending on the scale of between these two parameters, the description can be very different. And with these two deformations, it's not integrable, but still there are some substantial research on this subject.
Indeed.
So I'm wondering whether your deep has any meaning in that point of view.
I see. The only thing I can say for now is that these dips are roughly speaking, the place where bootstrap is poorly performing in a sense. So you can think of this as kind of complementary approach to the basically the field theory approach where you turn on the mass term and the magnetic field term, right? In that case, which is generically termed Ising field theory, for example, Jamolozhikov studied this using the truncated conformal space approach. And yeah, there are actually interesting bootstrap bounds at the level of the field theory using the S matrix bootstrap, because now the system is non-integrable. There are massive excitations, and one can talk about the S matrices of those massive excitations. And that S matrix actually have nice bootstrap results, I guess, in the work by Shi and Barak Gabay several years ago. Yeah. So this is, in a sense, somewhat complementary. This is performing well away from criticality, basically.
Okay, so I have one more question. So
sure.
When H is non-zero, you showed that this correlation result only with the E1, just nearest neighbor. Do you have a similar result of S0 and S2 times E1?
Great. So single S, I actually didn't display, is for example here.
No, that's single. But my point is a 2-point correlator. But the distance is not single unit, but two.
Okay. Yeah, actually, I didn't plot it, but it can be easily plotted. Yeah, and the bounds are still good. Yeah, the bounds are still good.
It will be interesting to take a log and then take a ratio to see what happens to the ratio of the correlation.
Yeah, I think you have in mind the fall off of the correlator.
Yeah, it will be falling off, although it is small distance.
Sure.
That's why I was asking the accuracy.
Sure.
And this ratio should be given by one of the lowest mass of E8 spectrum.
Right. Indeed. Yeah, it's going to give rise to the mass gap or some estimate on the mass gap. Indeed.
Yeah.
Any other question? I have a simple question. Can you count some random magnetic field? And in that case, is there some? Can you do this bootstrap for that case?
Very interesting question. So by random magnetic field, I have in mind for, let's see. Yeah, this H. Now you are also having some distribution of H in front.
Yeah.
Yeah. So first of all, I don't see why positivity would fail. Positivity will be still valid. And the relations are still going to be valid. I think it's even going to be a simpler problem if one wish. If one can actually do the randomizing the magnetic field in some analytic way. Yeah, I mean, I didn't think about it, but to me, it seems like I'm not losing anything that are essential for the bootstrap. Yeah, thank you.
So any other question from the online audience or offline? If not, let's thank speaker again.
Thank you very much.
The Changmin will give the closing remark.
So thank you for your participation. And in during this week, we heard very many interesting talks and several related fields, including today's talk, and also the covering a wider subset from string theory duality to even Stedman and condensed matter and so on. And actually, this is our goal of this year, that we want to expand our scope of the research from traditional TT-bar oriented subset to its applications and also some other exact result and such as duality and so on. And thanks to all the participants and also online audiences, I think we achieved our first goal to diversify the subject. We want to continue this tradition in next year to have a bigger scope and better result. And also, I want to thank Junggi, who had done most. And this is thank you. Okay, so if you want to say something,
No,
please.
no, that's all. Yeah, thank you very much for all of you. Yeah, see you next year again.
Yeah.